I'd like to go over some concepts for acidic and basic solutions with you for reinforcement, particularly with some things that we seem to be getting confused still. So one of the things that I think we need to look at a little bit more closely is the difference between ionic and covalent compounds. If we look at a water molecule, there are covalent bonds between the two hydrogens and the oxygen. If we look at sodium chloride is a salt, and its molecular structure will never be just one sodium atom or one chlorine atom. These are ions that are attracted to each other because of their difference in charge. But what we will always have is we will have a network of these two charged atoms, which we call ions, stuck together in a very fixed structure, because this cation right here is stuck in between these negatives on all sides. This negative ion here is stuck in between these positive ions, and it's these attractive charges that keep these particles together, which is why when we have salts, they're always solids at room temperature. And they're very, very hard to heat up because these attractions keep these atoms in place. If we look at water, on the other hand, water is made up of multiple atoms that are sharing bonds. So a water molecule has two hydrogens and one oxygen. Here we see where hydrogen, which on the periodic table has an atomic number of 1 because it has one valence electron, is sharing one of oxygen's valence electrons. It has 1, 2, 3, 4, 5, and 6. Oh, well, this is saying from hydrogen, so let's pretend then that these are hydrogens electrons and that these then are oxygen's electrons. So in any case, we have the hydrogens that are sharing these electrons. So you'll notice that what would be this spherical orbital for these electrons and the spherical orbital for oxygen's valence electrons, they overlap. And in the picture, you can kind of see where there's an overlap there. And if we look at these two pictures, you can tell that these models also demonstrate there's an overlap between where these valence electrons are, because they're shared in between both, and these two do not share. These valence electrons stay within their orbit. These valence electrons stay within their orbit. They do not mesh together, but they do here with the water molecules. And there's some consequences to that. Some consequences are salts are crystalline in structure, they're solids. Covalent compounds, because they are sharing and these electrons are constantly moving in between the atoms, they are actually squishier. They can flow around past each other more. They're not stuck together in a rigid structure the way that ionic compounds are. They can't move. They're stuck in that structure because of their attractions. But water molecules can move around each other. They're always going to move and orient so that the positive end of one is going to be attracted to the negative end of another. But they're free to move. They can flow around each other. They're just always going to stop in an orientation where their poles, nope. There we go. Where there's always going to be, there we go. There's always going to be attractions between a partially negative side and a partially positive side. So the oxygens are partially negative, the hydrogens are partially positive, and these attractions are going to determine the orientation, how they're going to be facing each other. But they can still move around. They still have that little bit of freedom to move around, and their attractions will change with them when they move around. So they can move around a little bit. These can move around. And so as a consequence, whoa, who are you attracted to? There, you're going to be more attracted over here. So as a consequence, covalent compounds can be liquids and even gases at room temperature, where ionic compounds are going to be solids because they're not sharing these electrons. There's no back and forth. There's no squishiness with those substances. But when we put them together, Remember that water is very unique because although it is covalent and it does have that squishiness that most covalent compounds, or that flowiness that most covalent compounds will have, it does have that partial positive and partial negative. So it can interact with an ionic compound, and it can come in here and it can start, let's see, oh, that's negatively charged, so yeah, it'll be attracted to the cation. And if enough of the water molecules attract, then they'll be able to pull, and it's always going to be the oxygens that are attracted to the cation. If enough of these surround the cations and anions, then they can pull that apart, and that's how we can dissolve ionic compounds. And then we have a whole bunch of other things that can happen with water. Because water has a very unique property. It can auto-ionize or self-ionize. And so this is a good thing. If we haven't written it down in any other pieces of notes, this is something good to have written down. The auto-ionization of water produces equal amounts of hydroxide and hydronium ions. Right, so there are a couple of ways to look at this. Let me show you what's really happening. When we say auto-ionization, produces hydroxide and hydronium ions. What we have is water, and we just saw another illustration of how we have a partial positive side and a partially negative side. Well, remember that we're sharing here. These electrons are being shared, and so sometimes this oxygen can pull those electrons to it to such an extent that we might have this hydrogen atom jump onto another water's oxygen. So now we'll have one water molecule that actually has 1, 2, 3 hydrogens in it, and that's our hydronium ions, that's what that is. And then we'll have this water molecule that's no longer a full water molecule, it's lost one of its hydrogens, so now it's a hydroxide ion. And that is auto-ionization. And so we can have that occur, and then we'll have our hydroxide is negatively charged because it's lost a proton or a hydrogen. And then we have the hydronium ion that has an extra hydrogen. So what's interesting is a lot of times we simplify this. And even when we talk about pH, it's really the power of hydrogen that we're talking about, when in reality it is the hydronium ion that's present. But this is how we simplify it. If you look at what a water molecule is two hydrogens and an oxygen. And we just finished talking about net ionic equations, where we said if you have the exact same thing on both sides of the reaction, then you can cancel it out as a spectator. So sometimes what we will do for simplicity is we will say, well, we have an HOH present here, and we have an HOH present here. Well, couldn't we look at that and say, hey, this was a spectator, the HOH here was a spectator, so let's cancel that out. And that could actually simplify our equation to water breaks down into a hydroxide ion and what's left? A hydrogen ion. And that kind of makes sense because if we had these, well, opposites attract. So this negative would attract that positive, and if we had 2 hydrogens together with 1 oxygen, then we have H2O. So this is a simplification that we sometimes use. And when we talk about acids and bases, we're really going to be talking about the formation of these hydrogen ions and hydroxide ions that are present because of interactions with other cations and anions. Okay, so acids and bases. So for the demonstration that we have set up, I actually got some help from Skylar. There she is. She set up these well plates for us, and she did some of these litmus paper testing. And so we have these pictures. Thank you, Skylar, for helping us set that up. So what I'd like for you to do is, if you're doing this for class, for a grade, then we need to copy down what is in these different well plates and leave some room in each of these wells to write down your observations for when we test these. So let's go ahead and do that. We've got sodium hydroxide and we have hydrochloric acid. These are our controls. I know that this is going to act like a base. I know that that's going to act like an acid. Distilled water should be neutral. And then we have Kool-Aid powder. and a Kool-Aid solution, powdered soap, and soap solution. And then we've got some household substances, bleach, vinegar, orange juice, and we put ammonia in that last one. It's not on there right now, but we did have ammonia. So you can add that on there as well. And so what we did was we used a pH paper, and this is what those samples look like. And the first batch we used red litmus paper, and if you'll pause and write down your observations for what we have. The base turned the litmus paper blue, the acid turned the litmus paper pinkish, and the distilled water just made the paper wet. That's all. It didn't really change anything. It just got a little darker because it was wet. And then you notice that the powders didn't have a reaction. So those are good observations to make, write down. And then we also did litmus paper that was blue. And we saw that the base, again, turned that paper blue. So whether it's red litmus paper or blue litmus paper, bases will turn paper blue, litmus paper blue. Acids will turn the litmus paper pink or red, we say. Distilled water, anything that's neutral, won't really change pH paper. Again, the powders don't do anything. It's only the solutions that we will see a reaction with. And we do have another type of indicator. And so remember, when we talk about indicators, we're talking about these things that change colors. These are two indicators here. And the first one is phenolphthalein. I know that's a mouthful, but phenolphthalein is a really good indicator if you have more base than acid. And so you can see how it definitely makes a difference in what the bases look like. But if you look at the other samples, it doesn't look much different from what we started with maybe the exception of the bleach, which is such a strong oxidizer that it actually just bleaches the color away. So I would call that term bleach. But everything else that was a base, we could see that there's a definite reaction. With universal indicator, we can actually tell whether something is relatively acidic or basic, or alkaline is the other word that we could use. And so you'll see that the Kool-Aid didn't really change color because it was already reddish to begin with, but the base, once we had that liquid universal indicator, we could see that it was basic. If we had the solution, it is a greenish color. So in the green area is leaning towards it being neutral at pH 7. Bases are on the blue end of the spectrum, which kind of falls in line with the pH paper, right? Bases are blue, acids are red. And so you can see a relative strength of the pHs. And so there's another way that we can use indicators. And so this actually here is pH paper. And what they've done is they've soaked it in the universal indicator. And so you have now a paper that will do the same thing that last well plate showed us. So these different colors here, we should see a similar distribution of those colors down here. And then there's always a scale that they give you to let you know about what pH these things are by matching up the colors with what it is. For example, we could tell that the Kool-Aid and the hydrochloric acid are very acidic because their pinkish reddish color is very close to here. Okay, so there's that. These are good observations. You can pause and go back to them if you need to. We do have some questions that should be answered. If you're doing this for a grade, you'll want to pause, write down those questions, or even discuss them if you're doing it as a class. But I do also want to go back and remind you that we didn't see anything with the powders. We did see things with the solutions. And so remember that things have to be in solution in order for them to act as acids or bases. And so a quick reminder on a couple of these things is remember that we do have to have water present. So the hydrochloric acid doesn't automatically break down into itself. It has to have that water molecule that is polar to go in and take away that hydrogen, and then we form a hydronium and a chloride. And that's what's reacting with the pH paper. The same thing happens with bases as acids. Once they are placed in water, those ions separate. And strong acids will do that completely. They will completely dissociate, while weak acids will only partially. So there will be less available hydrogen ions to react with those indicators.